Hello, my name is Alireza Mortazavi. I am a graduate student from Johns Hopkins, and this is the work that I'm doing mostly in collaboration with my advisor, Jennifer Lotz and Josh Barnes, and also other members of our group, Greg Schneider and Mike Peth. So we are trying to dynamically model galaxy mergers because we want to know the initial conditions of these galaxies before they started to merge, like the orbital parameters, and then if we can get the distribution of these orbital parameters for a sample of galaxy mergers, we can compare it with the orbital parameters of dark matter halo mergers from cosmological simulations. This shows the distribution of eccentricities in dark matter halo mergers by Benson, 2005. So it's also it's been shown that the rotational properties of the remnants of these galaxy mergers depend on the initial orientations of these disks. So slow rotators are usually the result of retrograde mergers, while fast rotators are the result of prograde mergers. Also, merger-induced star formation rates depend on the orbital parameters of the mergers. Pericentric distance, and this is from T.J. Cox's paper 2008, which shows the dependence of the star formation, merger-induced star formation rate on the pericentric distance and on the inclination of the disks. So how do we do the dynamical modeling? So people usually try to find the most similar model to the galaxy. So this is from the famous paper, Tumra paper of 1972. He's trying to model the mice galaxies. So basically, people are doing the same thing these days. The only difference is that they also look at the kinematics of their model and try to match it with the kinematics of the data. So this visual matching has some disadvantages. It needs a lot of human time to go over all these different models with different parameters to find the best model. It is subjective. It depends on who does this matching, and it doesn't have a well-defined uncertainty. So the question we are asking here is there a better way to do this? Meaning, if we can make an automatic approach with a more quantitative measure of the quality of the match, and more importantly, we want to have measurements of orbital parameters with uncertainty, with well-defined error bars. So the tool that we are using is called Identikit. It's a software for modeling and matching galaxy mergers. It's been developed by Josh Barnes and John Hibbard, a newer version by Josh Barnes in 2011. So it's combining test particle and self-consistency techniques to be able to go over the parameter space in a relatively short amount of time. It provides us with the kinematics of the data, and so what you will do then is to make a library of Identikit models. So you put these galaxies in different orbits with different mass ratios, different eccentricities. You look at these at different time steps. So you have this library of Identikit models, and you try to match them with your data. Identikit, the newer version of Identikit actually provides us with a measure of the goodness of the fit. It's called score. And in order to calculate the score, you put these boxes on the tidal features of your galaxy, and then Identikit will go over the parameter space to find the best model that can populate these boxes, these phase space regions. So if you get a model from your library of Identikit models that has wrong parameters, wrong orbital parameters, you'll get a bad match with a bad score. And then if you have a good model, you will have a good match, visual match, and a better score. So then you can make something that we call the score map. And each point in this score map is actually an attempt to match one of the models in your Identikit library to the data. So you just, and this is of course a multi-dimensional space. I'm just showing a two-dimensional slice, pericentric distance versus time. And so you just find the maximum in the score map, and that would be your best fit model. However, we still don't know what's the uncertainty of the score. So in order to calculate the uncertainty of these scores, we start to move these boxes around, and each time with each set of boxes, we get a different score map. We do this several times, and 100 times specifically, and then we take the average of these 100 score maps, and then the standard deviation, which will give us a measure of the error on each point in the score map. And then we can make these contour plots, which is, this cyan box is going to be our best fit model, and the contours 1 sigma, 3 sigma, and 5 sigma shows how far each point in our parameter space is from the best fit model. And this is another way to show this. So the color code here is from best fit to 8 sigma from the best fit, and this box is again showing the best fit model. This red box is actually the correct answer, and I'll come to this in a minute. So again, I said this is just a two-dimensional slice of the score map. Score map is multidimensional, of course. It depends on the parameters that we want to explore. And this is other slices of the score map, pericentric distance, eccentricity, time, velocity scale. And so the extent of this white region is basically telling us the error of our measurement. So we have developed this model that is automatic, and it's also providing us with an error bar on the measurement of each of these orbital parameters. And we can apply this tool on the data that we have. We have obtained the internal IFU data for many of these optical, and there are also archival radio data for many of these galaxies. There are also more data coming up with the future surveys, kinematic surveys. So we can apply our modeling method to the vast amount of data that is going to be available soon for nearby galaxy mergers. But before that, we want to know, is this method for modeling galaxy mergers working? And by that I mean, so of course we obtain an answer with an error bar, but we want to know if this answer is close to the correct answer. So in order to do that, we use an independent set of simulations, gadget simulations from the TG Cox, the 2006 simulations, which was provided to us by people here in Santa Cruz. And then we use different components of these gadget simulations to explore the different kinematic tracers. This is the list of the simulations. We explore gas and young stars. We explore different pericentric distances, different eccentricities, different orientations of the disks, prograde versus retrograde, phase-on versus edge-on, and different time steps of these simulations. So we want to know how well this method is working for each of these. So I'm going to explain the results or describe the results very fast. Unfortunately, these retrograde and polar models, tests, didn't work very well. So our model didn't converge on an answer, and we're still trying to figure out why. But for the rest of these tests, this technique worked, and I'm just going to go over the results. This is showing the answer. This is what I showed earlier. This is the answer or the score maps for the fiducial model, and it's with the gas. Sure. So I'm just gonna skip this and go to our summary plots. So I'm here plotting the best fit time, fractional time, versus the correct time that we already knew for these gadget simulations. And as you can see, we are doing a quite good job on constraining the time. This is basically the merger stage. This black line is the line that we're supposed to get the answers on, and as you can see, these points are following the line. I should say that the blue points are the tests with the gas, and the red points are the tests with young stars. So this is for the eccentricity. Most of the gadget simulations that we used had the same eccentricity. They were on parabolic orbits, and we are actually finding them very well, the correct answer for them. We also tested a few elliptical orbits, and as you can see, we can find the elliptical nature of these orbits as well. However, we are underestimating the eccentricity. And this is the results for the pericentric distance. Again, most of the models that we test had the same pericentric distance, so that's why they're all piled up on the same corner of the plot. So as you can see, except for a few of them, we can say roughly up to two orders of magnitude whether the model that we are testing, the galaxies that we are testing had a small or a large pericentric distance. So this is my summary. So we have made an automated algorithm for based on identikit to calculate or to measure the orbital parameters of galaxy mergers, and this also gives us the uncertainty of these measurements, which is very important. We have tested our models against gadget simulations. It seems that our results show that this method is very good at finding the right merger stage. We can also do relatively good jobs on eccentricity and pericentric distance. However, we didn't find the right answer for the retrograde models, and we have to figure out why. Probably it's because we are only using the tidal features as to find the right answer, and the retrograde mergers don't have as strong tidal features. And so we have to probably look at the rotation curves. And we are ready to apply this method on our data, starting with the mice galaxies. Thank you.
Alireza, while Peter sets his computer. Who wants to result the tool? Sandra.
You mentioned there are some differences between what you put in and what you kind of get out.
Mm-hmm.
So, do you plan to make your algorithm to learn about this so that we can correct for this kind of?
Yeah, that's what we're trying to do. So so if the differences are, so probably we have to work more on the results and try to digest them very well, better, so we can find if there is a trend, specific trend, and we can correct for those biases if we can find them. So yes, for the time, for example, you could see that there is a little bit of overestimation of the time, so we can correct for that clearly.
So in your identikit versus identikit one, it looked as if the original input was often much more than 1 sigma ruled out by the in your fitting. So it's looked like it sometimes be 1 and 5 sigma or whatever. Presumably, it's reasonable to renormalize the sigmas or it's. I mean, if you get more than if you get 3 sigma 68% of the time, it's like, well, I guess 3 sigma kind of means 1.
Mm-hmm.
To which extent do you think that that's a reasonable thing to do, or is it telling you that there's other parameters that you're not really able to search for? Because you have uncertainties, but it looks like they're underestimates.
Actually, I don't get what do you exactly mean by the identikit versus identikit, because we have...
The original thing, we had the blue and the red dot,
Mm-hmm.
and the red dot was at often the 5 sigma.
Yes.
That didn't strike me.
So yes, that was for a specific test.
Sure.
So for the
5 sigma should never happen.
Mm-hmm. So I think that would be our systematic bias. So probably if we can find that these biases are all in the same direction, we can fix for that. And for the time, we know that for the merger state, we know that this bias is always in the same direction. But for the pericentric distance and eccentricity, probably we have to also.
Thank you, Alireza. I'm sorry.
Like path. So we are trying to dynamically model galaxy mergers because we want to know the initial conditions of these galaxies before they started to merge, like the orbital parameters, and then if we can get the distribution of these orbital parameters for a sample of galaxy mergers, we can compare it with the orbital parameters of dark matter halo mergers from cosmological simulations. This shows the distribution of Hello, my name is Alireza Mortazavi. I am a graduate student from Johns Hopkins, and this is the work that I'm doing mostly in collaboration with my advisor, Jennifer Lotz, and Josh Barnes, and also other members of our group, Greg Schneider and Mark. So how do we do the dynamical modeling? So people usually try to find the most similar model to the galaxy. So this is from the famous paper, Tumra paper of 1972, which is trying to model the mice galaxies. So basically, people are doing the same thing these days. The only difference is that they also look at the kinematics of their model and try to match it with the kinematics of eccentricities in dark matter halo mergers by Benson, 2005. So it's also it's been shown that the rotational properties of the remnants of these six galaxy mergers depend on the initial orientations of these disks. So slow rotators are usually the result of retrograde mergers, while fast rotators are the result of prograde mergers. Also, merger-induced star formation rates depend on the orbital parameters of the mergers. Pericentric distance, and this is from T.J. Cox's paper 2008, which shows the dependence of the star formation, merger-induced star formation rate on the pericentric distance and on the inclination of the disks. So